Hello students, and this video will prove the Liouville Approximation Theorem for transcendental numbers. So this is Liouville's theorem. It says, suppose that R is a root of this equation, an x to the n plus an minus 1 x to the n minus 1 a1 x plus a0 equals 0. In other words, I gave you the solutions of a polynomial equation where these coefficients where a0, a1, an are integers, okay? So in other words, this root r is going to be an algebraic number, right? So here r is an algebraic number, okay? Then there's a constant c greater than 0, such that for any p and q and z, either r is equal to p over q, so either r is that rational number p over q, or r minus p over q is bigger than or equal to a constant over that number q to the degree of the polynomial n. So either one of these two things happens over here, right? So here's our proof of this fact. So this is a very analysis-y proof. So proof. Okay. So let's suppose r is a root of, let's call this equation over here star, is a root of star, and p and q are in z. Okay, let's find an interval. So find an interval 0 less than r. So let's do like this, minus y less than delta. So I'm going to look at an interval. I'm going to look at all points y are within delta units of r, such that on this interval, such that p, our polynomial over here, so let's call this, let's give our polynomial a name over here. So let's call our polynomial something. Let's call our polynomial over here, I'm going to call this function over here f of x for our polynomial, such that f of y is not equal to 0 on this interval, on r minus delta, r plus delta minus the point r itself. It's a deleted interval over here, okay? So we know that polynomials have a discrete number of roots. So near a root, I can find a small enough neighborhood where there's not going to be any other roots in that neighborhood because the zeros or roots of polynomials are discrete, okay? That follows from the discrete fact that the polynomials are real. On this interval, so on this interval, since f prime is continuous, it's still a polynomial, right? There is an m. We know that the maximum f prime is bounded on this interval. That interval over there. So in other words, on that interval, we have the f prime of y is less than or equal to a constant m over here. Okay? So in other words, on this interval, there are no other roots of my polynomial, and the derivative is bounded on that interval. That bound will obviously depend on delta, right? That's fine. Okay? All right, excellent. So now let me suppose that y is a rational number, not equal to r in this interval over here. So if p over q is not equal to r, and p over q minus r is less than delta, then what can we say? Then, well, what can I do over here? So let me plug in that p over q into my polynomial over here. So if we plug in this so since p over q is not equal to r, and it's in this, we know that this polynomial will not evaluate to 0 on this. So what can we conclude from that? So we'll be able to conclude that an p over q to the n plus all the way down to a0 is not equal to 0, which also implies that an p to the n by multiplying by q to the n plus all the way down to a0 q to the n, so I multiply both sides by q to the n, right, is not equal to 0. But now, since p and q are integers, that is a non-zero integer, which means it has to be larger than 1 in absolute value. So an p to the n plus all the way down to a0 q to the n is bigger than or equal to 1. Now I can divide by what? I can divide by q to the n again and conclude what? I can conclude by dividing by q to the n that the absolute value of an p over q to the n plus all the way down to a0 is bigger than or equal to 1 over q to the n. Okay, excellent. And so now what can I do? So now, of course, that's the value, that's f of p over q. And since f of r is equal to 0, I can conclude that f of p over q minus f of r, since that's equal to 0, is bigger than or equal to 1 over q to the power n. Okay? Now, by the mean value theorem, this is no more than the largest of the derivative, right? So by the mean value theorem, 1 over q to the n, which is less than or equal to f of r minus f of p over q, is less than or equal to the largest the derivative can be, m, times the difference of r and p over q. Okay? So in other words, the difference of p over q minus r is bigger than or equal to 1 over q to the n times m. So that's the estimate I want. That's the value of c if what? If you're less than, if p over q minus r is less than delta, right? However, if you're in the opposite range, if p minus q, p over q minus r is bigger than or equal to delta, they're far away separated, then what does that say? I can make this bigger. P over q minus r is definitely going to be bigger than or equal to delta over q to the n, because q is a fraction. So in other words, I'm making this whole expression over here, what? That's a number, so that's even smaller than delta itself, right? So in other words, this estimate is true if you're outside that region. So in other words, what we can choose for our constant c in this theorem can be chosen to be whatever this is, the smaller of those two numbers over there, the minimum of those two numbers over here. So whatever one is smaller will get the result. So the minimum of 1 over m and delta will be the choice of c that will exist, and that proves our theorem. And then in the next video, what we'll do is we'll see that we can use this result, this Liouville theorem, this approximation theorem, to show that Liouville's number is not an algebraic number, that is in fact transcendental. Thank you very much.